Welcome everyone to this screencast, or what we should call it, where we will discuss the energy transport by radiation. So this is an attempt to reach out to you while we are all in lockdown. So please make sure to let me know if this works better than by just reading the lecture notes for yourself. So the topics we will cover in this lecture is the introduction to radiation. We will talk about the net heat flow when we have radiation entering and leaving a surface. We will have a discussion on the nature of radiation before we end with some fundamental radiation laws that are applied for black bodies. And these are the Stefan Boltzmann's law, the Planck's law, and Wien's displacement law. The sources for today, or the source, so to speak, is the second compendium, which is called Radiation, and we will cover chapters 3.11, 3.1, and 3.2. So we'll start with a brief introduction, and the most important point related to radiation is that it is the only way that energy can be transferred between two surfaces which are not in contact. That is, they can even be separated by vacuum. The radiative heat transfer is due to electromagnetic waves. That means that radiation essentially will travel at the speed of light. That is 3 to the power 8, or 3 times 10 to the power 8 meters per second. Our planet receives quite a lot of solar radiation per day. The number is as much as 1 kilowatt per square meter, as long as we are in direct sunlight, originating from the total of 60 megawatts per square meter emitted from the sun's surface. Radiation is by all means a multidisciplinary topic, and it includes electromagnetic theory, thermodynamics, quantum mechanics, and statistical mechanics. So this is in a large extent covered by physics, but we will try to extract the metallurgical relevance from it in the following lectures. We'll start with a diagram describing the net heat flow. And we will revisit this diagram in the coming lectures, so then we will re-include it several times. And what we'll be looking at is a surface that has an area AI. So this is sketched in the bottom part here of our diagram. And we will separate between radiation entering and radiation leaving this surface. The first term we introduce is the irradiation. And for the irradiation, we will use the symbol capital G. And the irradiation reaching a surface I, we denote with GI. This quantity is a flux, so it represents energy per time per area, or watts per square meter. So the incoming total power, that is in watts, is simply the area of the surface multiplied with the irradiation GI. Here illustrated with this incoming ray. Another property of relevance is what we call the radiosity. Sorry about that color, that came out bad. The radiosity in green that we have here represents the corresponding outgoing flux, and multiplied with the corresponding area we get the outgoing power. Now the radiosity has two contributions. As we see in this figure, it has a contribution epsilon times EBI, and it has rho times GI. The first term is related to what we call the black body emissive power, which is here in orange and here and here. This we can think of as the surface's own ability to emit energy by radiation. Each of the surfaces we will consider, we can visualize as having a sort of coating. This coating has two effects. One of it is that it will reflect some of the external radiation coming in. It will go in and then it will be reflected outwards again. Also, this applies for internal rays. So the emissive power of the surface itself, some of it will be reflected back into the surface itself. The ability of the surface to reflect energy or radiation is given by this material property rho, which we call the reflectivity of the surface. We'll come back to that also later. So in the radiosity, we see here that we have a term which is rho I GI. That's the part of the incoming energy that is reflected due to the reflectivity of the surface. Correspondingly, we have a surface, or we have a property here, which is epsilon I, we know here also. This is the so-called emissivity. That's how much of the emissive power which actually escapes and is emitted. So the sum of the emitted radiation and the reflected external radiation gives us the radiosity. Final property here is this alpha. This is also related to the coating of the surface. This tells us how much of the incoming radiation is absorbed. We call this the absorptivity. So some of the incoming radiation is absorbed, the other one is reflected, as we have already seen. We can also define a net heat flow to this, or from this surface actually, depending on the sign. The net heat flow given here is given as the area, of course, multiplied then with the radiosity, which we have here, and the irradiation, which we have here. So here we see that if the radiosity is greater than the irradiation, that means that this difference will be a positive number, and the net heat flux will be positive, meaning that the surface is outputting positive energy into the system itself, which is now here. We'll come back to this in greater detail in the future lectures. Before that, we will have a look at the nature of radiation. And the prime feature is that radiation is both a particle and a wave. So we're straight into quantum mechanics already. And from wave theory, we say that radiation is a wave which is oscillating, vibrating if you want, with a frequency nu and a wavelength lambda. And this wave propagates with a velocity which is c. The velocity of this wave train is the frequency times the wavelength. This of course then corresponds to the speed of light. Correspondingly, we have in particle theory, where we say that, well, our radiation is actually particles of light. We call these light particles photons. These particles move at the speed of light, and they have a specific energy, which we use lowercase e for. And the value of this energy in joules is h times nu. Nu is still the frequency, and h is Planck's constant, which we have given here. It's 6.63 times 10 to the power minus 34. So this is probably the smallest natural constant that we have. Its units are joule seconds because we're multiplying it with a frequency which has units hertz or per second to give us joule in total. On to some of the general features of radiation. One important point is that the high frequency or short wavelength photons, and why I say this is that, well, C equals lambda times mu. So if you have a high frequency, then your wavelength has to be low if the speed of light is to stay constant, right? So high frequency or short wavelength photons, they have more energy than those with low frequency, and we also see that from the energy perspective, where we said that the energy equals to Planck's constant, which is a constant, times the frequency, so energy is directly proportional to frequency. The next point is that if you start heating a body, electrons will be excited. And that means that they're essentially jumping into higher orbitals. As these electrons fall back, they have to release their energy in some way, and typically this is done by emitting photons. These photons will have an energy, again, Planck's constant times the frequency, corresponding to the energy difference between the orbitals in question. So if you have the nucleus of your atom here, and you have sort of your high school orbitals, if you have an excited electron in this orbital that decides to fall back to a lower level, it will emit a photon that has energy Planck's constant times the frequency. And the energy corresponds to the energy difference in these orbitals. In addition to this excitation mode, radiation is also emitted due to vibrations in a crystal lattice. And these vibrations depend upon the temperature of the body as well. However, these energies are not discrete in the same sense as the energy emitted from the orbitals are. They are distributed over a spectrum of energies. And of course, energy is still equivalent to frequencies, so we can plot it as a function of frequency as well. This is the spectrum in question. And you've probably seen this before. We go from very small wavelength or high frequencies here, where we have gamma rays, to very long wavelength or low frequency, long waves, radio waves, microwaves, etc. In the middle here, let's see, let's use it in blue, we have what we call infrared, visible, and ultraviolet waves. And this is analogous to thermal radiation, which will be the main point of interest in this part of the course. In the very short wavelength, that's again the high frequency domain, so high frequencies over here. We have X-rays, and the X-rays are often created by bombarding a metal with a stream of accelerated electrons. And then we have on this side the radio waves, as I mentioned, that are generated by various oscillatory electrical circuits typically. This is a additional schematic showing the various types of radiation that we have. Again, here we have the frequency, and then we have the wavelength. And we have the cosmic radiation, gamma radiation, etc., ultraviolet, visible, infrared radio waves, as we have discussed previously. What is interesting with this table compared with the previous one is that we have the application in metallurgy here. So this is taken from the compendium. These forms of gamma radiation are hard and soft X-rays. As I said, we have thermal radiation, which is here, which goes slightly from the ultraviolet and into the infrared. Microwave ovens, dielectric heatings for furnaces, for example, and induction heating finally down here. So radiation, not only thermal radiation, is really important for our field. As I think I mentioned at least, the main focus in our course is on thermal radiation. And as we can see in this table, thermal radiation goes from around 1 micrometer and up until just below 1 millimeter. See what I wrote here? I wrote from 0.1 micrometer to 100 micrometer, so it depends slightly upon who you ask. This could have been 6, this could have been 3, but it's in that range at least, covering at least the visible light and extending slightly into infrared and ultraviolet. One important point is that thermal radiation is emitted from everything that has a temperature greater than 0 Kelvin. So that means essentially everything. And as I mentioned previously, it can propagate through empty space. An interesting feature about thermal radiation is that its intensity is determined by its temperature and thus condition of the surface, so the surface condition. So these two properties are of prime interest. And of course, surface conditions themselves are also something that we can control when we produce our metals. So this is sort of a two-way effect. The surface condition itself controls the radiative properties, but if we are able to control the surface properties, we can of course make the surface radiate as we want as well. So the first thing we will discuss is the so-called black bodies, shown schematically here. So this particular black body is actually green, but it should have been black. And the definition of a black body is that it will absorb all incoming radiation and it will emit all possible radiation as well. And the reason why we need this sort of definition is that not all bodies emit or absorb the same amounts of energy. And a black body is an idealization, or a reference if you want, to which we can compare other radiative bodies. As mentioned, a black body absorbs all incident radiation and emits all possible radiation. When we're talking about references, it's also useful to know what the opposite is. The opposite of a black body is a white body. The white body has no absorption and thereby no emission either. Real surfaces are somewhere in between. And typically we will denote these as gray bodies, because gray is somewhere in between black and white. More about that in the next lecture, either that you will read yourself or that I will read to you, depending upon the feedback on this one. So now we'll move on to the different radiation laws, and we will start with the Stefan Boltzmann's law, which is the one we will be using the most in this course. Stefan Boltzmann's law governs the total heat flux emitted by a black surface. And it states the following: EBI equals to sigma times Ti to the power 4. And if you recall the figure that we showed in the first pages, all of these quantities are fluxes, so the units are watts per square meters, or joules per second per square meter. In this particular formula, Ti, bad color again, sorry, let's do it in blue. Ti to the power 4 is the temperature of the surface I, so the surface that we're looking at. And this sigma is 5.67 to the power minus 8. Okay, that's a constant you can remember, 5, 6, 7, 8. This constant is the so-called Stefan Boltzmann's constant. Its units are somewhat awkward. It's in watts per square meters per Kelvin to the power 4, and that's to be able to get rid of this 4 that we have in the law itself. Stefan Boltzmann's law gives you the total radiative flux. One thing it doesn't do is to explain how this energy is spread over different wavelengths. This was, however, resolved by Max Planck in the 1900s, which relates us or brings us to Planck's law. So Planck's law tells us something about how the energy is distributed. It gives us the so-called spectral or monochromatic emissive power density. So I'll get back to what I mean with the power density shortly. It's not energy per kilograms, but it's still called the power density. We'll see it shortly. The formula that we're looking for, or that Max Planck derived, tells us the following. This thing here, which is then the spectral energy density, is equal to 2 times Planck's constant speed of sound squared divided by the wavelength to the power 5 times 1 divided by this exponential function minus 1. The exponential function takes a few parameters, some of which we know already. It's Planck's constant, speed of light, wavelength, Boltzmann's constant, and finally temperature in Kelvin. This is normally written as A divided by lambda to the power 5, because the only thing which is sort of a variable here is this lambda. Everything else is lumped, so 2hc squared is A. And then in the exponential function, we lump everything except wavelength and temperature into this coefficient B. The units for Planck's law is watts per square meter per meter. So it's a flux per meter, and this per meter describes a range of wavelength. Particularly, it represents how much energy you have, or how much the energy flux is between some wavelength lambda and lambda plus delta lambda. So this is essentially a small interval. And the reason why we have this over a small interval is that we have this magical thing d lambda, which we of course can introduce into an integral. We could integrate these over all possible wavelengths and then get the total energy flux. As mentioned here, the heat flux, total heat flux, is obtained by integrating over all wavelengths in question. So if we want to do this, all possible wavelengths will go from 0 to infinity. And this will then correspond to what we have already introduced as EB. That will then simply be the integral over all possible wavelengths of the spectral energy density multiplied by this d lambda. So this is watts per square meter per meter, and this thing is then, meter squared, but meters. So in sum, this will come out as a flux, watts per square meter. So in this step, we have just introduced Planck's law in the integral. And in order to solve this integral conveniently, at least, we have to do a substitution. The substitution is as follows. We substitute b over lambda t with x. Then if we solve that particular equation with respect to lambda, then we can see that our d lambda equals minus b over x squared t times dx. So that would be the input into our integral. If we now do this substitution and move things that are constant outside of it, we are left with an integral which is not entirely trivial, but it is sort of a standard integral that you can look up in a table. Either Rotman, for those of you who are native to NTNU, or you can use Wolfram Alpha, for example. And you find that this specific integral from 0 to infinity equals pi to the power 4 divided by 15. Great number. So the integral EB as a function of t comes out as pi to the power 4 over 15 multiplied with alpha over b to the power 4 times t to the power 4. And this factor here is what we had in front of the integral originally. If you write this out, you get the following expression, which is neat. And as I mentioned in the introduction, this total flux calculated from Planck's law must correspond to that of Stefan Boltzmann, because it's essentially the same thing. In Stefan Boltzmann, we had that the energy of this black body, so there should be a B here, equals to sigma times temperature to the power 4. And if you look at what we had here, we had something times t to the power 4. That means that this something has to equal sigma. As I've stated here, sigma equals 2 times pi to the power 5th times the Boltzmann's constant to the power 4 divided by 15 divided by Planck's constant to the power 3, and then the speed of light to the power 2. And this is what had the remarkable form of 5.67 times 10 to the minus 8. and that was watts per square meter per Kelvin to the power 4. I think this is my favorite constant. It's a remarkable formula because it couples radiation, which then is Stefan Boltzmann's constant, the sort of basic principle or the first law of radiation, if you want. It couples that to thermodynamics because we have Boltzmann's constant. It couples it to general relativity because we have the speed of light, but it also couples it to quantum mechanics. It couples it to quantum mechanics to Planck's constant, which essentially describes features that are happening within the nucleus and within the atoms. Planck's law can also be visualized quite conveniently. What we have here again is the flux density as a function of wavelength for objects with different temperatures. So the blue one here is an object or a black body at 300 Kelvin. The green one is one at 1000 Kelvin, and the yellow one is at 3000 Kelvin, and finally the red one is at 6000 Kelvin. What you can see here is that the different black bodies at a different temperature will emit radiation in a different range. In particular, we have this band which is here, and well, it has a rainbow in it, and it's because this is where we have visible light. And here we see then that, well, the object which is at 1000 degrees here, that has sort of a tail going into the visible light. So this is one of the objects we will start to see glowing, or we'll start to see the objects glowing when they reach around 1000 degrees. Whereas this object here, which is at 300 Kelvin, does not have any tail going into the visible light, so we won't be able to see the temperature field of such a object. Of course, blazing hot surface of the sun is visible to the naked eye, as we all know. So the final law that we're going to look at today is Wien's displacement law. And the displacement law states the following. It states the following. The emissive power density, EB lambda, that we have derived from Planck's law, has its maximum at a wavelength which is inversely proportional to temperature. So that means that the maximum that we have here, so we have maximum here, 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 and here, these maxima are inversely proportional to the temperature of the object in question. The way we derive this, since we're looking for a maximum, and a maximum depending upon a wavelength, we will take the derivative of this power density with respect to lambda and set it to 0. And when that is fulfilled, the wavelength that we find will be the wavelength corresponding to the maximum point of the energy. So the way we do this is that we just plug in Planck's law into the derivative, carry out the derivation, put it equal to 0. That gives us, after some manipulation, the following expression, which you can solve with respect to lambda. Remember that B here is a constant depending upon various things. So we can plug in the numerical value and we can find the following expression. So lambda equals roughly 3 times 10 to the minus third over t. And that is Wien's displacement law, the wavelength at which you get the maximum power density is inversely proportional to temperature. One feature of this is that the maximum of the power density will shift toward the lower wavelength when temperature rises. So this is, as I mentioned roughly a few minutes ago, at 300 Kelvin you'll have no visible light because the whole curve is in the high wavelength region. If we go to this green curve, this has, as I said, a tail that goes into the visible light. What's interesting with that is that the largest wavelength for visible light is in the red region. So this thing here will appear glowing red. As we hopefully know, if you've heated anything in a furnace, you know that it will turn red before it starts to glow in other colors. For instance, if we go to 3000 Kelvin, this has a broad amount of energy within the visible spectrum. It will be glowing white, because white is sort of the superposition of all colors. It will maybe appear more yellowish actually, because it has larger part of its energy, or the high energy part of the spectrum is towards the yellow and red, while this final one at 6000 Kelvin sort of has its maximum in the middle, so it will be even contributions from lower and higher wavelengths, and that will definitely then glow in the white color. The practical consequence of Wien's displacement law is that if you then are able to identify this particular wavelength at which you find the maximum density, you are able to determine the temperature of your body. Of course, provided that it is black, because that has been the fundamental assumption that we've done for the description of these laws. That was it for this lecture. I'll appreciate your feedback to whether this was an okay way to do it or not. Since it takes some time, if it's not worth it, then I won't do it simply. But if you enjoyed it and you found it useful, then I will continue doing it. Thank you.